Hello everyone. In this lecture I shall discuss the existence and uniqueness criterion of Laplace transforms. If we recall the definition of Laplace transform, a function ft t greater than is equal to 0, the Laplace transform of ft is given by L of ft is integral 0 to infinity e to the power minus st into ft dt. Right. Now if you integrate it, here s is a parameter here. So in place of t we are going to substitute 0 and infinity. So this will be a function of s only. Here s is real, s greater than 0 and s in r, real number. Okay. So now this is subject to the condition. This is subject to the existence of the integral. Right. Existence of the integral. Right. Not all integral with the infinite limit exist. So the existence of Laplace transform depends upon the existence of this integral, and we have a special criterion for existence is known as the sufficient condition. I will explain shortly. Before that, let me to introduce myself. Professor Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology, Burla, Sambalpur, Odisha, India. Okay, so let me to write the existence condition. Coming to the existence condition, a function ft be such that ft is piecewise continuous. And secondly, ft is exponentially ordered or bounded. That means bounded, we can say at infinity. Bounded at infinity. That means ft mod less than m e to the power some kt, right, and t greater than some constant c. At infinity we are talking, so however large t, and here m and k constants, and these constants are to be known constants, or we can find it, the value of this. Then L of ft exists. Provided your s greater than this constant k, right? S greater than this constant k. As long as s greater than k, then this Laplace transform exists under these sufficient conditions. The condition is sufficient, not necessary in the sense, note that the condition is sufficient only. The conditions is sufficient only, but not necessary. What does it mean? Even if these conditions, that means even if the conditions not hold, right, still L of ft exists. For example, suppose you have a function f of t is equal to 1 by root over of t, right? The function is not piecewise continuous. Ft is not piecewise continuous at 0. In fact, at 0 it has infinite discontinuity. Right? However, L of ft is L of t to the power minus half is equal to gamma of minus half plus 1 divided by s to the power minus half plus 1. So this is gamma half by root s. So gamma half is root pi and it is root s. So therefore L of ft is L of t to the power minus half is your root over of pi by s. So you see here. Thus this condition 1 doesn't hold. Still we are getting this. That's why we say this condition is sufficient only. It is not necessary. Okay. Beyond this condition also there are functions of which we will able to get the Laplace transforms. Now we will discuss two more important things. What is piecewise continuous and what is exponentially ordered in details. Okay. Coming to piecewise continuous. Let me write the definition. Now coming to the definition of piecewise continuous function. A function is said to be piecewise continuous on an interval if it can be subdivided into finite number of subintervals on which the function is continuous on each subinterval. Right? Continuous on each subinterval. We should write each open subinterval. Right? Each open subinterval. And at the end points, it should have the finite limit. Right? For example, suppose I have a function like this. You say the greatest integer function. Right? You see. So the function is, here it is continuous and here it is a jump here. Again continuous and jump. This is the example of a piecewise continuous functions. Right? The function is like this here. Here we have a jump and here we have a jump. So the function is piecewise continuous like this. Okay. These are the example of the piecewise continuous function. However, at this jump point, it should not be infinity. Right? It should not be infinity. So this is the definition of piecewise continuous function. Now coming to the definition of exponentially bounded. Exponentially bounded. As we have pointed out above, here ft mod less than me to the power kt. Right? A function ft is exponentially bounded if ft mod less than equal to some me to the power kt. M and k known constants. Okay. And which is equivalent to say limit t tends to infinity ft divided by e to the power kt mod tends to 0. Right? This can be also the equivalent aspect of exponentially bounded function. You see, if we bring this here to this side and we can verify it. Okay. And it is as long as here s greater than k. As long as s greater than k. Okay. So now how a bounded function and an exponentially bounded function related. Coming to a bounded function. Right. Coming to a bounded function. Here ft mod is less than is equal to some m, or I can say this is equivalently ft mod less than equal to some m e to the power 0 into t, is not it? If I write it some k, if I write it some k here, then it is your k e to the power k. So what is the value of m here? M is k and k is here. So you write suppose some lambda you write. Suppose you write some lambda. So here m is my lambda and here k is here 0 as per the definition. Right? So that's why this is exponentially bounded. So every bounded function, right? So every bounded function is exponentially bounded. However, the converse is not true. Converse is not true generally. For example, if I have ft is equal to 2 to the power t, right? It is not bounded, right? Not bounded. However, However, it is exponentially e to the power 2 ln t, right? It is of the form e to the power kt. So this is exponentially bounded, right? So that means this is your bounded function, and this is exponentially bounded function. So exponentially bounded function has a larger scope, right? Bounded implies exponentially bounded. So exponentially bounded has larger scope, right? Larger scope. Now coming to an example, find the constant m and k such that t to the power n and t to the power n sin at is exponentially bounded. You have e to the power t is given by e to the power t. What is the expansion? 1 plus t square by factorial 2 plus dot 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 t to the power n by factorial n plus dot dot dot. This is summation n is equal to 0 to infinity t to the power n by factorial n. So you see, so now this is t to the power n by factorial n, and these are the positive terms here. Okay, so individually this e to the power t is greater than equal to t to the power n by factorial n. So that means your t to the power n is less than is equal to factorial n e to the power 1 into t. So you see here what is your m here? So m is factorial n, and what is your k here? K is 1 here. Okay, similarly here t to the power n, right? T to the power n sin 80, right? This mode is your t to the power n, which is less than is equal to factorial n e to the power t. So m is equal to factorial n and k is equal to 1. Also in both cases, right, Laplace transform exists. Note that every polynomial function, right, every polynomial function is exponentially bounded, right? Every exponential function, you can say of degree n is finite, is exponentially bounded and has Laplace transform, right? And as also polynomial function is piecewise continuous, right? So coming to one more example, ft is equal to tan t, cot t, secant t, cosecant t. Are these functions piecewise continuous? Are these functions exponentially bounded? Of course both are no. You see, coming to ft is equal to tan t, this is sin t by cos t, right? It doesn't exist at cos t. Cos t is equal to 0 implies t is equal to 2n plus 1 pi by 2. So the denominator is 0, cos t is equal to 0 at t is equal to this. So here ft tends to infinity, right? So these are the point of discontinuities here. Also here you will get the vertical asymptote here, right? So the function is not piecewise continuous. So not piecewise continuous. Moreover, coming to the second point, moreover here tan t by e to the power at mode, if here limit t tends to pi by 2, it tends to here infinity, right? Means at finite point it gives us infinite value. So it is not exponentially bounded, right? Not exponentially bounded. Here also in all these cases, right, Laplace transform doesn't exist here, right? Laplace transform doesn't exist. Only sin t and cos t, only the trigonometric functions where Laplace transform exists, right? So coming to more examples of existence and non-existence, I can write it as follows. Coming to two more examples, ln t minus 1. So these functions Laplace transform doesn't exist. You see these functions have singular points, have singularity, right? In this case t equal to 1, ft tends to infinity. So here ft tends to infinity when t less than equal to 0. So Laplace transform doesn't exist here. This is not piecewise continuous, right? Not piecewise continuous, right? So these functions, it is yes piecewise continuous. Second example, yes piecewise continuous, but this piecewise continuous rational and irrational numbers are dense in R. So even if it is piecewise continuous, but infinitely many discontinuity, right? So Laplace transform doesn't exist here, right? Coming to one more example. So example, suppose e to the power t square, right? E to the power t square, it is not exponentially bounded, not exponentially bounded, because here exponentially bounded means it should be ft mod less than e to the power some me to the power kt. It should be of this form, right? So it is not exponentially bounded, and Laplace transform doesn't exist here, right? Coming to an important result, in line with the previous sufficient condition, let ft be piecewise continuous and every finite interval, and satisfy this means exponentially bounded for constant m and k, then L of ft exists for s greater than this k, okay, and L of ft tends to infinity as s tends to, L of ft tends to 0, say, tends to 0 as s tends to infinity, tends to 0 as s tends to infinity. So if we think of the proof of this, right, what is L of ft? So your L of ft is integral 0 to infinity e to the power minus st ft dt. If I take modulus here, right, which is less than 0 to infinity e to the power minus st ft mod dt, okay, bringing modulus to inside here. So I can write it integral 0 to infinity e to the power minus st ft mod dt, and ft mod is less than equal to 0 to infinity e to the power minus st, it is m e to the power kt dt. So you can write it integral 0 to infinity m e to the power minus of s minus kt dt. If you integrate it, it will be 1 by s minus k, right? Here s is greater than k, and when limit s tends to infinity, this 1 by s minus k is equal to 0. So what we are getting? Limit of LFT is 0 when s tends to infinity, okay? So this is the condition. So only trigonometric function sine and cosine has the Laplace transforms. Coming to some important note, sin t and cos t are the only trigonometric functions which are piecewise continuous as well as exponentially bounded and has Laplace transform. But these functions do not have Laplace transform, right? Have no Laplace transforms. Tan t, cot t, sec t, cosec t. In fact, they are not exponentially bounded, even they are not piecewise continuous. Find m and k, coming to an assignment question. Find m and k so that this is exponentially bounded, and find the Laplace transform of this. You see, here t square e to the power minus t, t square e to the power minus t, these are all continuous. So this implies t square e to the power minus t is also continuous. Every continuous function also implies piecewise continuous. Moreover, what will happen to this? Here f of 0, ft is t square e to the power minus t, f of 0 is equal to 0, and limit t tends to infinity, ft is equal to limit t tends to infinity, t square by e to the power t, here tends to 0 by L'Hopital rule, right? So ft is bounded, so that means ft is, every bounded function is exponentially bounded, right? Now we have to find m and k. We can think of the maximum value of this, right? What is your ft? Your ft is t square e to the power minus t. And what is f dash t? F dash t will be 2t minus t square e to the power minus t is equal to 0, implies t is equal to 0 and t is equal to 2 into t minus 1 minus t is equal to 0. It is here t into, if you simplify it, here t into 2 minus t is equal to 0, t is equal to 0 and t is equal to 2. F of 0 is here 0, but f of 2, this yields your maximum value. F of 2 will be, if we substitute it here, it is 4 e to the power minus t. It will be here 4 e to the power minus 2, right? Minus 2. So what we can say? It is m e to the power kt, right? M e to the power kt. So this will give you m is equal to 4 e to the power minus 2 and k is equal to 0, right? And what is the Laplace transform of this? L of t square e to the power minus t will be factorial 2 by s to the power 3, with s is replaced by s plus 1 because of the shifting theorem. It will give you 2 by s plus 1 whole cube. Okay, so this is your answer. In subsequently we will discuss the uniqueness of Laplace transforms, right? We will discuss the uniqueness criterion.